loss base b s equal 1 divided by that.
Say again?
We can change by like 1 divided by loss b s.
I think so, yeah.
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 One. Yeah. One.
Sure. Yeah. All right, there's a sign-in sheet.
Thanks for that tip.
Yeah, yeah.
I forgot my map.
Check it out, make sure it works. Don't trust my memory.
Okay.
I think it works. All right, so questions?
It works.
Cool.
Okay.
All right, well, we were talking about Hashmaps Wednesday. So remember, the basic idea of a hash is, or one way to implement a hash is an array of key value pairs. And we can just use an array. We can just take your keys and store them here and store the values next to them. And then when you want to look for something on a key, you can just search through your list of keys until you find the key. And it's going to look like a hash to an outside user. But the idea of a hash is that when you take a particular key, there's something called a hash function that will tell you where in this set of parallel arrays that key should be stored. It's not guaranteed to get you there the first try, but it should get you there quicker than just starting at the beginning and checking every single entry until you find your key. So it tends to be order 1 rather than order n. That doesn't affect how we use a cache though. To us, a cache is just this abstract data structure that we can go in with a key and say, give me the value that's stored there. And it's exactly what we do with an array, except with an array, our keys are always integers. We can say, give me what's at location 5, give me what's at location 2, and so on. A hash is like a generalized array where we can index with things that aren't integers. And there's numerous implementations of hashes. The two main ones we're going to work with are hash maps and hash tables. And they're almost exactly the same except for a few details. Hash maps let you have nulls as values and also as a key. So if you want to store something that is null associated with a key, you can do that in a hash map. You can't do that in a hash table. The advantage of a hash table is it's what's called thread safe. If you run code on multiple threads, multiple processes that are accessing the same hash table, you're less likely to get into trouble than if you use a hash map. Trouble in the form of different things trying to read or write the same locations at the same time.
So we can do modulus.
So you can do what?
Modulus.
It's something inside is probably doing that, but we don't have to. In fact, there's no way that we can.
I'm sorry, what was the difference between hash tables and hash maps?
It gives you a little synopsis up here in the beginning, but basically hash maps will let you have null values. Hash tables don't have nulls, but they're what's called synchronized, so they're thread safe. They're easier to work with from multiple processes. Neither of those are really going to affect us in any serious way. Yeah.
That makes it like thread safe.
Yeah.
Like what's like the mechanism that ensures that?
Well, so we're gonna start this next week, but I kind of started it already in the morning. So let's talk a little bit about the thread idea. You know how to do forks in C, right? You can say fork, and fork comes back and it either gives you a 0 or a process ID. If you're a child, you get a 0. If you're the original process, you get the process ID of the child. And now you got 2 copies of your process running, identical except for that return value from fork. And then usually they differentiate in some way using that return value. The effect is, you start off, you've got some main program running, and at some point another thread is created, and maybe at some point it'll create another thread, and these could create other threads, and so you may find that there's multiple processes running. So classic.
That's the idea behind our 5th project.
Yeah, that's going to go on a lot in the 5th project. We're going to have possibly up to 5 threads in there, or more. So word processor example, right? This might be the thread that is waiting for you to type something. This might be a thread which is kicked off when you need to save your file, so that you don't have to wait while the save is taking place. It can write in the background, but you can still keep typing. This might be a thread that, I don't know, is getting news information or something relevant to you and displaying it. And so there's this problem. If these threads are totally independent of each other, no problem. They can just go off and do whatever they want. There's potential problems if they're trying to share information. For example, you have some variable x which is accessible by all of these different threads. And this might write a value into x, and shortly after, this might overwrite that value with a different value of x. Well, maybe that's okay, because they each have a right to think that they have the value of x that wants to be written. And so that might not be a problem, but think about this scenario. And this is part of what we're going to spend talking about next week. So, and processes in Java are called threads. It's just terminology. So here's thread 1, and here's thread 2. And you can create objects that are accessible by both of these, so they can communicate by sharing information in a variable. It's basically shared memory. So let's suppose that some stuff happens, and somewhere thread 1 wants to increment the value of x. So x is, some piece of memory that's shared. Maybe this is counting the number of times that something happens. So something happens in thread 1, it wants to increment the value of x. Something happens in thread 2, and at some point it wants to increment the value of x. Okay, this looks fine until you think about what's going on at a lower level, at something closer to an assembly language level. So, not all processors can increment a random memory location. Sometimes to increment a memory location, you have to read that memory location into a local register, and then there's an instruction for incrementing that register, and then you can write that register back out to memory. Okay, so this is a read, modify, write operation. And even though it looks like we're saying just add 1 to x, we're really reading x, we're modifying the value we read, and then we're writing it back into x. So let's look at that. So x equals x plus 1, maybe in assembly language or bytecode, this says copy x to local register R. And then increment register R. And then copy R to X.
It could potentially go out of bounds.
Out of bounds in what way? You mean overflowing?
Maybe.
Could. That could happen.
Or if your X is used in an if statement, it would never be. None of the if statements would run because X would be out of the normal range.
That's possible too.
Is there a third thread that handles all the information set?
You
You can make a queue and type into it and make it see, oh, this one wants to increment. Okay.
that's going to be one way to deal with what we're about to do. And we're going to talk about it a lot next week, and there's strategies for coping with this, and that's one way is to have some sort of centralized arbitrator, what we're going to call a weight person in the dining philosopher's problem. If we don't have that, yes, x can go out of bounds, but there's something worse that can happen. So let's suppose that x is equal to 5. Okay, thread 1 executes. It says copy x to local register R. So R is equal to 5. And then it says increment R. So R becomes 6, and then we copy R to x. So x is equal to 6. And now thread 2 comes along and says copy x to its local register R. So R equals 6. Increment R is 7. Copy R to x. Now x is equal to 7. That's what we would expect would happen, right? Both threads incremented x. It started off at 5. Now it's going to be equal to 7. Okay, consider this. Suppose x starts off at 5. And thread 1 says copy x to the local register R. So it says R equals 5. And then it says increment R. So R equals 6. And at this point, thread 2 starts executing, because you've only got one CPU. So thread 1 has run for its quanta of time, and now the operating system says, okay, hold on thread 1, we're going to run thread 2 for a little bit. Thread 2 starts executing, it gets down here, it says copy x to local register R. So it sets R equal to 5. It says increment R, that's 6. It says copy R to x. That writes a 6 into x. Thread 2 finishes, thread 1 goes back to running. Where was it? It was right here, it was about to copy R to x. So it says, okay, R is equal to 6, let's copy that to x, and x is 6. And both threads have executed x equals x plus 1, but x changed from 5 to 6, not 7. That's a really annoying problem to try to find and to try to deal with unless you have some sort of help for dealing with it. And so that's the kind of thing that happens when you're not synchronized. Now, to synchronize it, you need to prevent this situation, right? You need to make sure that while this thing is doing x equals x plus 1, this thing doesn't interrupt it and start doing x equals x plus 1. And the trick is, if you can make all of this what we call atomic, so what does atomic mean? What's an atom? Go back to Greece.
So the relation go from 1 to 2, like x equals 5. Copy gonna be copy up, copy 5, and increment gonna be 6.
Mm-hmm.
Go to gonna be copy the 6, and increment gonna be 7.
Yes, that's what you would like, right? So that this, once this starts, it finishes before anything else can start, right? So atoms are these indivisible things that the Greeks theorized. If you keep smashing matter down to smaller and smaller pieces, you get to something that can't be divided anymore. So atomic operations can't be split up into any smaller pieces. In some sense, even though there's 3 things happening here, it's a single thing that can't be divided. So all you got to do is guarantee that once you start this, nothing else tries to monkey with x until you're finished. Well, how do you set that up? One way would be to try to use a flag. So when you're about to start executing your code, you raise a flag and say, I'm dealing with x, nobody else touch it. And if this thread comes along and is about to execute this code, it checks the flag and says, oh, I can't touch x yet. And it'll wait until that flag goes down, and then it'll go ahead and execute x. But how do you implement the flag? And if you try to actually code this, you find exactly the same problem. First, you check to see if anyone's got a flag raised, and if they don't, then you raise your flag. Well, if you both check at the same time and you don't see a flag raised, you're both going to raise your flag at the same time, and now you both think you have exclusive access. And it's a squirrely problem, and ultimately there's usually some kind of support in the hardware level itself. So on a MIPS processor, there are these atomic read, modify, write operations that you can use to implement this. In the JVM, it's a virtual machine, so they implement their own mechanisms to ensure that these operations can be made atomic. And we'll use a keyword called synchronized that can actually take entire blocks of code and protect it from this. And it's pretty easy to deal with. And so that's the kind of thing, like when you see something's not thread safe, like swing is not thread safe, it means you have to worry about this yourself.
So you could have a queue of threads and go like that.
You could have a queue of threads. You start to worry about performance issues somewhat. I mean, if every thread can just kind of do its own thing and run freely, you're going to get better performance than if you're really, really tightly controlling what every thread does. So you'd like to restrict that control to just the areas where you can have problems like this. But knowing where those are, that's part of the trick of doing multi-threaded programming.
So you can run again.
You can do that, and we're going to get into some interesting scenarios because this is only one type of issue, right? There's also questions of things like deadlock.
Programs
So-
that don't finish.
Programs that don't finish, programs that can't finish. So, so thread 1 and thread 2. So thread 1 is doing some stuff, and then it says, I need to get exclusive access to the keyboard, and then I need to get exclusive access to the mouse, and then I need to do some stuff, and then I can release the mouse and keyboard. And thread 2 is doing some stuff, and at some point it wants to get the mouse, and then do some other stuff, and then it wants to get the keyboard, and then it's going to release. Alright, so here's the keyboard, here's the mouse. And neither of them are in use yet. So thread 1 starts to execute, it does some stuff, it gets down here and it says, hey, I want the keyboard. And so the system checks, is the keyboard available? Yes, so it says, okay, keyboard belongs to thread 1. Meanwhile, thread 2 is running, it does some stuff, it gets down here, it wants the mouse, mouse is available, mouse gets allocated to thread 2. Thread 1 runs a little bit more, gets down here and it wants the mouse, mouse is in use. So thread 1 stops right here, and it's not going to go any further until it can get access to the mouse. Thread 2 runs a little more, gets down here, it wants the keyboard, keyboard's not available. It's going to pause right here until it can get the keyboard. And now you've got a deadlock situation, because neither of these threads can make any progress. Alright, this is waiting for something this has, and this is not going to release it until it gets something that thread 1 has. And you're stuck.
You can't release mouse until the program is finished with mouse.
Right, which is not going to happen until it gets the keyboard.
That's kind of confusing.
That's very confusing, so that's a deadlock situation. And this, you find situations sometimes where you've got code running 24 hours a day, like on a server, and it's working fine for a week, a month, and all of a sudden one day you come in and it's just like locked up and nothing's happening. And you might have stumbled across a deadlock situation. And the chance of this happening might be really, really small, which makes it really annoying to try to find that bug, because it's hard to reproduce. You just know that once a week or so when you come in, your system is hung, and that can be tricky to debug. So there's also live lock, and live lock is similar to deadlock. Live lock is sort of when you're walking down the street and someone's coming towards you, and you both move in the same direction to the other side of the sidewalk, and then you both move back to the first one. And you're changing state, but you're not getting any further in your larger goal, which is to move further down the sidewalk. And that can happen here, for example, after a certain amount of time, it might give up the keyboard and go back up to the top, and this might do the same thing and go back up to the top, but they might encounter the same deadlock situation every time that they go through. So we'll talk more about those things next week. And it's a fun but potentially,
Hazardous.
yeah, and maddening area to explore. But we'll look at some code where we can use these kinds of things to get some unexpected behaviors
That we want?
that we want to see. Probably that we don't want. But we'll play around with that next week. So hashes. When you create a hash, right? Remember, we've got this basic model in mind of a set of arrays with buckets, and your key gets hashed to some location in this array. So there's some notion of initial capacity. Yeah, thanks. There's some notion of initial capacity to this hash, right? How many keys can it store? And with Hashmaps, when you construct it, it picks some reasonable capacity to begin with. There's also a notion of how full is the hash. Remember, if the hash table is mostly empty, chances are when you pick an arbitrary key, it's going to hash to a location that's available. And you get this nice order one behavior. Hash to a location, grab your value from there, or store your value, or delete it. But as the table fills up, as more and more of these locations are occupied, your chance of collision starts going up. And so the load factor is basically the ratio of how many cells are occupied versus free. So when your load factor is 0.75, 3/4 of your spaces are full. So you can specify what kind of load factor you want to tolerate before the hash is expanded. So by default, it's got a capacity of 16 and a load factor of 0.75. And when it becomes too full, it will expand the hash table. So it'll make a new hash with a larger capacity. It'll rehash the things that were already in the old hash. And now you've got more space and your load factor has dropped. Alright, so let's play with this. Alright, so hash maps, they're generics. When you construct, you specify two parameters, the type of the key and the type of the value. So let's just go with string and string. So that should construct. So let's just make a list of teachers and what they teach. So Izad does 253. I don't know if she really teaches 104, but we'll pretend. All right, so there's some teacher data, and it's going into our hash. Alright, so we'll prompt for some input. And as long as we haven't hit end of file, We'll read a line from the user. And let's see what the value is in the hash table associated with that key. So we're going to say map.get, and the key we're going to use is just name, and that should return a string. And let's just print that out.
You don't do a hashmap or hash.get.
I do a map.get where I say string course equals.
Is that a function within the hash? Oh, map is a hash map.
Map is a hash map, and hash map should have a get, which will take a key, whatever type of object our key is, which is a string. So that should be good.
Scanner.
And I'm gonna need scanner, and I should probably close it too. I don't think I have to close it. Let's close it anyway. Just for fun. See if it compiles. Oh, not even close.
Ew.
Is it really called add? It's not called add. It's called put. Okay. That's better. All right, so who do we want to know about? Let's find out about Izad. Izad teaches 253. Carol is 104. Scott is 121. Nick is null, because not in the hash map. So if you go after a value that doesn't exist, it comes back with null.
Oh, we don't need to loop. It's the keep going.
So I got the code itself in a loop, yeah.
Where's the stored?
It's in memory. So if I exit, it's gone.
So you guys put it to a file if you want to store it?
Yeah. And yeah, and that's a number of ways we can do that. And if you put in a value with a key that's already got a piece of data with it, in other words, Izad was 253, if we also add engineering 250, it's just going to overwrite.
Is there a way to make it store as an array that will grab all of them, or a linked list?
Absolutely. Funny you should ask. Because when we construct this hash map, the first string that we're putting there is saying the keys are strings. The second string is saying the data itself is also a string. We could make that a linked list.
Yes. Everything is very reusable in here.
Isn't that strange? I wonder if it'll take that one construction line.
It doesn't.
Oh, I gotta import it though. Yeah, that's fine. That's just because I'm trying to add strings and they don't have strings. So there's construction of a hash map keyed off of strings, associating linked lists. So we got a few minutes. Let's try something. So let's read from standard in one word at a time.
Could you make the hashback place into an object that you made, or a class you made?
Could you make it what?
Can you make it place into like an object you made so you can create your own system of linked lists?
You mean have the hash created inside something?
Well, it says like string and then linked list. Instead of linked list, could you make your own object?
Yeah, you could store rectangles if you want, or fractions. It can be any object you want, including hash maps.
A hash of hashes.
A hash of hashes, definitely.
That's troublesome. And secure.
Yeah. All right, let's read a word from standard in. And if that word is not currently in our hash, let's put it in there. Map.put will associate with the word a new linked list of integers. So if we get a new word, we're going to put it into our hash, and it's going to be associated with an empty linked list of integers. And then what I want to do is grab the linked list associated with that word. That's a linked list of integers. And I'm going to say add last. Let's add the number of this word to the end of the linked list. So what are we writing here?
Pretty much what we did earlier.
This is PA2. We're not cleaning up the words, making them lowercase, but other than that, and alphabetizing, this is building a hash of linked lists instead of a linked list of linked lists. But when we're done, we should be able to put in a word, and it will tell us all the positions where that word occurred.
Okay, that's interesting.
Yeah.
With this, like, string dot equals.
I don't think I have any string dot equals in here. So how do we know if we've seen this word before? Because when we get a word, we store it in the hash table. So when we get a new word, we retrieve from the hash table using that as a key. And if we've seen the word before, it'll bring back something not null. If it comes back with null, we know we haven't seen this word before. So there we store the word with an empty linked list. And then either way, map.getWord will give us the linked list associated with that word. We call the add last method and tack the word number onto the end of that. So let's just see where the word hello occurred. I'm going to be a little surprised if this actually works. So I'm just going to call map.get. I'm going to give it the key hello. It should come back with a linked list, and if I just print that out, that should be the locations where hello appeared in the input. What do you think?
It will give you something very interesting.
So 1, 5, 8, and 9. That looks right to me. So there's a slightly simpler form of PA2.
That's slightly simpler.
Yeah.
That looks very simple.
Right. So this is what objects are all about. Right. Now, if we were doing PA2, we'd have to write the linked list class ourselves. Well, you did that. That was your location list, right? But then the thing that's using that is pretty slim. All right, so what if we want to see everything that's in our hash? Remember, with hashes, there's no inherent ordering to the keys. We can't say give me key 1, give me key 5, give me key 7. With arrays we can do that. We can start from element 0, and however many elements we have, we can get each element up to that number minus 1. With lists we can start with the first node and keep following. With trees we can start with the root and then say show me everything to the left, show me everything to the right. But with hashes there's no first or second entry. So we need some kind of mechanism for traversing a hash. And if we're the people who wrote the hash code, we might understand that this is a big array, and we've got, you know, a field here called valid, and we can go through, and any time that valid is set to a 1, we know we've got a key there, and we can print those out or whatever. But if we're coming at this as an abstract data type, where we can put and we can get and we can remove and we can search, right? We don't have access to that underlying structure. We need some way to be able to get a hold of the keys, and that's this method called keyset. So keyset is a method inside a hash map, and it returns something that's called a set. And a set is an even more abstract notion. Think sets as in discrete structures, just an unordered collection of things. Stuff has no natural ordering, but you can put things into here, you can remove things, you can search for things, and so on. And it's one of the more general versions of a place where you can store objects and retrieve them. And so we can use this key set method to get a set of keys. So let's look at all keys. So set all keys equals map.keyset. And set is also a generic type, so you have to specify what type of things you're storing in the set. And so this is actually set.
Is a generic its own class of things?
A generic means it's a class that can work with some variety of types. There's some aspect of it called a parameter that could be a different type of object. And so with a set, for example, we can say, do we want a set of strings, integers, rectangles, etc. And it's the same set class, but internally, if we retrieve an element from the set, it's going to expect it to be a string. If we create a set of type integer and we retrieve an element from the set, it's expected to be an integer. So the code is kind of agnostic to the type of objects you're using. So this is going to give us a set, and once we have a set, we have a method called iterator. And an iterator returns, well, an iterator. So let's make an iterator, which is also going to return a string. I'll just call it it. So that's all keys dot iterator. And once you have an iterator, it's got two main methods we're interested in, hasNext and next. So when you have an iterator on a set, here's what happens. Something goes in and it grabs the whole collection of things in the set. And when you say iterator.next, it's going to pick one out and give it to you. And the next time you say iterator.next, it'll pick out a different one and give it to you. And it'll keep doing this until you've given it everything that's in the set. And you can see if there's anything left by saying hasNext. So you can call iterator hasNext. If it's true, then calling next will get you another thing from the set. And if hasNext comes back false, the set's empty. Right, in the sense that you've seen everything that's in the set. So looping through this, is pretty straightforward. So while there's a next object, so we can call it.next, that gives us the next word from our hash, and then we can just repeat this print statement. So we'll print out next word, we'll say it occurs, and we'll print out the linked list associated with it. And then when has next comes back false, we're done. We've seen everything that's in the list, in the hash. Oh yeah, and I have to import these things. All right, ready? There we go. And I don't see anything double counted. That looks good. Cool.
That BA2.
There's PA2. Got to alphabetize. You lose 5 points. All right, so that's pretty cool, potentially.
How can I compare the each character compare?
Yeah, it's kind of subtle, because we don't actually compare anything to anything, right?
Yeah.
But when we say go into the hash and give me the linked list associated with hello, effectively it's the behavior is, every word in the hash is being compared to hello, and if one of them matches, then it gives us the linked list associated with that. Right, that's the behavior. That's not how it works, because it's a hash, so it knows where hello would be, and it just goes and looks for it. But basically, it's comparing hello against every word, and if it finds it, it gives us the linked list. If it doesn't, it will come back with null, which tells us it's a new word, and so we create a new linked list, and now we put that word into the table with that empty linked list, and the next time someone looks for that word, it'll find it. And so I think you heard me say this in 224, hashes are one of these giant sledgehammers that when I first discovered it, I just used it for everything. And it's a really powerful tool to code up all kinds of things.
And in a concise way.
In a concise way, yeah, because there's a lot going on inside these methods. So if you're writing an interpreter, right? So you want something like MATLAB that you can type in code and you can say execute and it runs it for you, but it's not compiling it and turning it into ones and zeros. It's just reading each instruction from your file and interpreting what it should do for each statement. And so if you have a statement like new count equals time plus offset. Right, so you've got some code written and you get to this statement and you parse it, you use scanf or something, and there's an equal sign, so it's an assignment statement, and you find a plus. So I need to get the value of time and offset, and I need to update the value of new count. Well, I'm an interpreter, right? So somewhere in my memory, I've got, new count is equal to 5, and time is equal to 11, and offset is equal to 8. And I need to say, okay, time is 11, offset is 8, 11 plus 8 is 19. Okay, and I need to update this to a 19. And your variables can be anything, right? Letters, numbers, underscores, things like that. Well, if you use a hash, you can store the values of these things just by storing them in a hash table, right? So I would have a table of variable values, and the symbol time, that string, would be associated with the value 11 for whatever reason, and offset with 8. And when I want to know what the value of time is, I just go into my hash map and I say get the value associated with time. And if it comes back null, then I know this variable has not been seen before, and I can either give an error or treat it as 0 or whatever I want to do. And so if you want to write something like bash, where you can do arithmetic, and you can have variables in your shell, you know, variable equals blah, 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 and then you can say $variable to see its value, right? You can use something like hashing to store those and be pretty efficient. And yeah, you can always do it with just a plain old array and just search through all of them and find the one that's equal. But if you think about it in this terms, where this value is actually associated with this string, right, it's a different mindset. And I think it gets you into some more interesting spaces algorithm-wise. So hashes are available, and they're useful for a variety of things. And there's more you can do with them than we've done here. But you can replace and update. Well, that happens when you add it anyway. You can find out how many things are in your map. You can also pull out all the values, right? Normally we're focused on the keys, but if you want to know all the things that are in the value area, you can pull those out and do a collection. A collection is like a set. And we can also get rid of entries. Remove. All right, does that make some sense? So my plan, roughly speaking, Monday is we'll start talking about multi-threaded behavior, and we'll talk about threads, how to make threads, and deal with all of that. And then later on, we'll start looking at some of these issues of deadlock and synchronization and so on. But we'll play around with threads. We'll have fun with those for a few days, and we'll use that probably in PA5. So we'll probably start talking about PA4. Midterm is Wednesday. We'll talk probably Monday or Tuesday. Probably Monday I'll go through like what you can expect on the midterm, which means I haven't written it yet, but I plan to write it over the weekend. So, all right, have a great weekend. Stay hydrated, and I will see you Monday.